Working more regularly with 40 plus megapixel files, I've been looking at ways of speeding up my editing workflow. Looking to upgrade, I was looking at principally two options in the near future to replace my Intel-based Mac. An upcoming Mac Pro based on the M1 chip, or a GNU Linux desktop built on AMD Threadripper. Principally, I want to know if, in my editing workflow, the switch to the M1 chip or its successor would speed up editing, or more generally, how would I expect performance to differ between each of these two platforms? I used darktable for developing my raw files, so I took my imported photos from 2019 and used those as test cases. Some weren't modified beyond the default modules, while others made use of computationally expensive modules like contrast equalizer or various noise reduction methods. While the benchmark is most concerned with darktable performance, I'm also going to touch on where and why you might generally see performance differences between each of these two platforms. And for reasons I'll get into later, we'll look at how the GPU performance and memory play an impact. Stick around. A couple of years ago, I did most of my editing on an Intel NUC with integrated graphics and 16 gigabytes of RAM. It was fine for 8 megapixel images and even 16 megapixel images, but it never felt snappy. Obviously, computers continue to get faster, and I figured I'd upgrade at some point. And a forcing factor being when I eventually moved to the Leica Q2 with its larger raw files. I figured if I needed more storage, I should take the opportunity to improve performance as well. I don't want to get too far into why I settled on Mac at this point. I'll come back to that, some of the pros and cons later. But I ended up replacing with a 16-inch MacBook Pro with a Radeon 5500M and a terabyte SSD. That's been working out well, but again, I hit the limit of on-device storage, and honestly, the lower-powered laptop components weren't as fast as I could get with a desktop. It's probably helpful at this point to understand what contributes to a smooth user experience in darktable and what's important to user performance. There are the basic steps of reading an image from disk and putting it into memory, but the bulk of your time is going to be spent rendering images. If you want to jump to performance charts, just skip forward to the appropriate time right there. Otherwise, I'll talk a little bit about darktable, followed up by talking about Apple's M1 chip. Things are a bit different if you happen to be using Adobe's Lightroom. Professional nonlinear video editors like DaVinci Resolve and Final Cut Pro will actually share closer optimization advice, but I'll touch on more of that later on. I'll talk about some of the ways of optimizing darktable performance after that, and if you want to just jump to some of the pros and cons of Mac OS X, that'll follow. Darktable affects a processed image by executing its rendering pipeline, which includes all the modules you've applied to the image stack. Things like levels, exposure cropping, and denoising. Some of these are really basic, but some of these are complex operations. And in order to minimize artifacts between stages in the rendering pipeline, darktable treats each and every pixel of the image along the way as a 32-bit single precision number. If you don't know what that means, it means big, heavy math. The type of math that CPUs don't traditionally do very well, and which leads to the development of special instruction extensions like MMX for Intel or AltaVec in the power lines. ARM chips like the M1 call their special sauce Neon, and generally these are known as single instruction multiple data instructions. These instructions are optimized, for example, to operate a single instruction efficiently on all the pixels in an image, the multiple data. Another side note here, the coolest name to these instruction sets, like so many other awesome things, came from SGI, the MIPS digital media extension, known less prosaically as MadMax. Of course, to really crank through these operations, you want to look towards coprocessors, special silicon made by companies like NVIDIA, or formerly ATI. It turns out graphics cards geared towards pushing out complex frames from video games quickly are quick at producing complex images outside of video games also. Now, this obviously isn't new if you're familiar with the industry. Expensive workstations have been using expensive workstation graphics cards for decades, and more recently, supercomputers performing complex simulations have been using multiple high-end cards because of how good they are at doing high-precision calculations quickly. The good news is that if you just want to speed up your darktable rendering, you don't need one of those astronomically expensive workstation cards. You're probably going to see better performance with the simply outrageously priced gaming cards. Generally speaking, the workstation cards are optimized to improve double precision or 64-bit floating point calculations. For simulations requiring extensive precision, those extra bits will pay dividends, but when you're mapping back to limited color gamut, it simply isn't going to matter, and 32-bit calculations are significantly faster, regardless of whether you have a workstation or a consumer class card. Darktable utilizes OpenCL, which is supported by the major graphics cards and operating systems. Its first commercial implementation was with Apple's OS 10.6 Snow Leopard in 2009, and despite Apple deprecating it in 2018 with OS 10.14 Mojave, it's still available on the integrated GPUs in their M1-based computers. Because Apple is deprecating OpenCL in favor of its proprietary Metal API, and based on discussions in the Darktable IRC channel and just general preference, at the start of the year, I started looking into switching back to a Linux desktop. At the same time, reviews of the M1-based Mac Mini were coming in with praise. I think the M1 chipset is exciting in a lot of ways, and I wish Apple were more open with the rest of their hardware so that the overall system could once again be solid Linux boxes. But those wishes aside, let's focus on the key benefits of the M1 and why it really is a better performing architecture for most people. Most users want a quiet and therefore energy efficient computer which performs normal to desktop tasks like web browsing and maybe traditional office tasks and basic media playing. Despite the efforts of web developers, these tasks aren't all that taxing, with most of the time involving moving information from disk or to the network into memory and having the CPU do something with it and then pushing that update to memory, disk, display, or whatever. The only special work beyond that, which really helps out the user, is speeding up encryption decryption for things like full disk encryption, like Apple's File Vault, or accessing secure websites, and optimized decoding for media streams like H.264 or H.265 for efficiently playing back high-resolution video from things like Netflix, Amazon Prime, or YouTube. The M was built on an extremely advanced fab process, which gives it better heat dissipation and power utilization compared to the current generation of Intel CPUs. Beyond that, there are architectural differences which play into the M1's favor. There aren't really philosophically pure RISC and CISC chips anymore, in part because of what we mentioned earlier with the desire to optimize certain complex tasks. Nevertheless, you may have heard that the M1-based Mac is a RISC or reduced instruction set computer, while Intel produces chips with a complex instruction set. What this means is technical, but importantly means that the M1 can do some fancy tricks not available to Intel or AMD x86-based chips because of the guarantees in the M1's instruction set. It can be much more efficient in processing upcoming instructions, while the AMD Intel CPUs either need to wait, guess, or rely on developers who tend to be pretty poor at this sort of thing. As a reminder, if you want to skip to the benchmark results, that time is back on the screen right here. Alright, so the principal differences are that RISC instructions are fixed length and need to access memory via load store commands, while CISC instructions need not do either of those things. This allows the M1 to more efficiently process instructions and confidently reorder instructions for better throughput performance automatically. Intel and AMD chipsets also perform reordering or out-of-order execution, but have much smaller amounts of memory dedicated to storing upcoming instructions, the reorder buffer. Again, the reasons for this are in part driven by the architecture itself, where reordering and speculative execution on CISC chips can lead to larger performance hits, penalties, when there's a misprediction, when the speculatively performed or predicted work ends up not being used, and the CPU needs to operate on some other data instead. In part because the process of simply identifying and processing instructions is more expensive in a CISC world. So there's performance benefits and choices made in the CPU instruction set and architecture. We also mentioned the advanced processes used to reduce the size of the M1 and its internal components, which reduce heat generation, thereby increasing power efficiency. Just as reducing the size of the CPU improves efficiency and overall performance, bringing things closer together does the same thing. We've seen mobile phones continue to shrink by bringing more components into the same package, the CPU, GPU, and memory. The M1 does this as well. The M1 fully embraces this by not only not needing to access memory across the North Bridge. Recent generations of Intel chips have moved this closer to the CPU as well, but by utilizing its unified memory architecture. Its unified memory architecture has a single pool of memory which can be directly accessed and shared across the CPU, GPU, and the M1's neural cores. With Intel chips, certain devices like integrated graphics may use the same memory as the CPU. The M1's implementation differs in two significant ways, though. The M1 uses faster memory than current gen Intel chips, and unlike Intel's architecture, the M1 just shares better. With Intel, effectively, the computer puts up fences and tells the CPU which memory is its and which memory is reserved for, say, the graphics card or GPU. In the Intel world, if you need to do some work on some data on the GPU, you first need to copy the data to the GPU section of memory, even if it's already there in the CPU section. This is relatively quick, but still takes time and adds up if you have to do it a lot. With the M1, the GPU can directly reference the same data the CPU is working on, which means you neither need to copy the memory into the GPU special area, nor back out to the CPU's area. There we are at the benchmark. So how does the M1-based Mac Mini compare to the 16-inch MacBook when it comes to image processing and darktable? Well, I ran with the latest version of darktable in both cases, built for x86, so it was running through Apple's Rosetta 2 translation layer on the M1 Mini. It would likely be faster if it were native, but there are a few dependencies just aren't available yet on the M1. And since we're also testing the OpenCL optimized pipelines, those actually probably won't see much of a change. Looking at the on-CPU performance only, the 16-inch's 8-core i9, 2.4 GHz boostable to 5 GHz, outperforms the M1 in raw throughput when looking at the total dataset. This is more pronounced the more memory is necessary, so we seem to be seeing the effects of needing to swap to handle the lower RAM available on the M1 Mini. This was the 8GB version of the Mini, and you'd likely see much closer performance if this were the 16GB version. In fact, in the low memory dataset, which comprised the majority of these images, the performance trends on CPU were basically identical. Let's look at how the dataset split and how Darktable performed once we moved work onto the GPU. The images are made up of Adobe digital negative files almost exclusively from the Leica X2 and the Leica Q2. In addition to looking at the overall dataset, I'd split them into low, medium, and high memory groups, roughly based on which cards would be able to fully fit the required data into their memory. 62.5% of the files needed about 1 gigabyte or less of memory, the low memory dataset, and any modern graphics card would have absolutely no trouble with that amount of data. Also, looking at the low memory group, we see very little difference between the M1 and Intel Core i9. Actually, there's probably a bit of an advantage with the M1 at this point. The larger memory available to the 16-inch allows it to pull ahead as the complexity increases. 37.1% of the images were in the mid-memory category. This is where most of the Q2 images ended up, with roughly 97% of the 47 megapixel images requiring between 1 and 4 gigabytes of memory when running on the GPU. Again, these will fit in any recent discrete GPU from AMD or NVIDIA. But ATI and NVIDIA did release OpenCL cards supporting between 1 and 4 gigabytes of on-card memory, and Intel Discrete Graphics only allocated about 1 gigabyte of memory. I didn't tweak any settings other than specifying the device for any of these tests. 8% of the mid-memory set comprised 60 megapixel images coming from the X2. About 1.2% of the Q2 images made up the high memory data set, just under the 1.4% of Q2 images which stayed in the low memory group. Because the sample size is so low here, the high memory group I think is interesting, but not statistically significant. Nevertheless, it does show some clear trends through the dataset, with the onboard Radeon 5500M and eGPU 5700 clearly leading the pack, and the M1 GPU clearly beating the on-CPU or Intel dedicated graphics. It's an interesting note that Darktable reported allocating up to 5 gigabytes on the M1 GPU, while only the 1 gigabytes on the integrated Intel graphics. The Radeon cards each had 8 gigabytes of memory. One interesting note here that caught me by surprise, given that the Darktable devs are principally focused on GNU Linux and Apple has deprecated OpenCL and Mac OS, is that there wasn't a noticeable, significant performance loss on Mac OS when compared to GNU Linux, either on CPU or using the Intel graphics. I used the same 2015 MacBook to test GNU Linux against Mac OS. Okay, those are the 1,000-foot results. Let's take a deeper look at what's going on here and what the expectations are if you're going to look to pick the best hardware for running Darktable or DaVinci Resolve or Final Cut Pro. What numbers on the spec sheet are most important? Well, there are the quintessential basics, and these are even more critical if you're condemned to Adobe. Fast memory, solid CPU, and disk I/O. Memory speed, latency, and bandwidth is currently a clear winner for the M1. If you're using Adobe Lightroom or Photoshop, the CPU becomes even more important since, based on other people's reports and benchmarks, it effectively added GPU acceleration as a marketing point rather than a performance feature. With Darktable or Professional NLE, you can significantly improve performance by offloading it to the GPU. How much depends on effectively two variables. How quickly can you transfer the data to and from the GPU, and how quick can the GPU do its work? For the latter, how fast the GPU is at doing the work, you can basically look up the floating point operations per second, and that's going to give you a good idea of where the card sits on the performance yardstick. Specifically, the metric that's relevant here is the single precision or 32-bit floating point operations. And they're usually either shown in teraflops, trillions of operations, or gigaflops, billions of operations. You want to make sure that when you're comparing cards, you're using the same unit or converting. Obviously, a 3 teraflops is 1,000 times faster than 3 gigaflops. That is, 3 teraflops is the same as 3,000 gigaflops. The current leader for a single card solution is the NVIDIA Ampere-based GeForce RTX 3090, which advertises about 35.5 teraflops if you can get your hands on one. I had hoped to test a Radeon 7 Pro, the fastest AMD GPU on the market and fastest GPU supported by Mac OS, but it's been on back order for several months now, and my initial batch missed. I'll see about adding it to the article on https nada.pro once it arrives and I can run the benchmark. But it only advertises 13.1 teraflops, or 36% of the floating point operations of the NVIDIA card. The older non-Pro variant, if you could get your hands on it while it was still shipping, was actually slightly faster, having been clocked higher, but with weaker double precision, that's 64-bit performance, which again doesn't matter for the programs we're considering. The cards we did test are all Mac OS compatible, and the floating point operations are taken from the manufacturer with the exception of the M1 GPU. Most people reference AnandTech's article where they estimate 2.6 teraflops, so we'll go with that. It fits the performance metrics, trouncing the 360 gigaflops of the integrated Intel graphics on the 16-inch MacBook, but falling short of its dedicated GPU, the Radeon 5500M, which boasts about 4.5 teraflops. We also tested the AMD Radeon 5700 built into the higher end of two recently released Sonnet eGPU breakaway pucks, which advertises just under 8 teraflops. For comparison, Apple used to sell two Blackmagic eGPUs on their website, one with the Radeon RX Vega 56 that offered 10.5 teraflops, and one which is still available using the Radeon Pro 580 which offers 5.5 teraflops. As you can see from the charts though, performance doesn't carry over perfectly. Unfortunately, we only had one eGPU here, making it hard to build a generalization, but we clearly don't see the expected nearly 2x performance boost going from the internal 5500M to the 5700 eGPU. Performance is flat. So what happened to those extra 3.5 teraflops? Again, without more data, it's hard to say exactly. However, going back to that other performance variable, how fast can we get to the data to the card and back? It's clear that the eGPU-based cards are getting hit here. Now, this has nothing to do with bandwidth, assuming your eGPU is directly connected to the PC and not sharing any bandwidth, and you have a high-quality, short cable. That's a lot of caveats, but basically the Thunderbolt 3 has plenty of bandwidth. Remember way back when we were talking about the M1 and why it was super fast, assuming it didn't just jump to the benchmark results? Well, the problem here is the counterpoint to how the M1 is improving its performance by moving things closer together. An eGPU is effectively moving the graphics card further from the CPU and memory, both logically and physically. This increases latency, which means getting data to and from the GPU gets a constant penalty added to it. The good news is this penalty shouldn't get bigger as the data gets larger, assuming you don't need to make additional round trips. You see, darktable will tile images that are too large to put into the card's memory, and this will lead to additional round trips. So being able to push and read data less often will show an improvement. When we look at the charts, we see the 5700 eGPU and its 8 teraflops actually underperforms all other options besides the Intel GPU on half of the images. By contrast, it and the 5500M were the clear winners in the mid-memory and high-memory datasets. So that brings us back to the question, GNU Linux or macOS, and if macOS, Intel or ARM? The operating system itself doesn't seem to make a huge difference. Again, there are some meta considerations which I promise I'll get back to. The real difference, though, is the availability of hardware support. NVIDIA's top-of-the-line 3090 is the clear performance king, breaking 35 teraflops, while the runner-up 3080 is much more affordable and still way beyond the nearest competitor, the Radeon 7 Pro, nearly 30 teraflops compared to just over 13. It's possible an upcoming Intel-based Mac Pro will support Radeon 7 Pro, or maybe 2, but that still provides less than 90% of the performance of a single RTX 3080. It's also worth noting, even if you happen to see an improvement in Adobe's Lightroom using a GPU acceleration, it'll only use a single card. Darktable and professional NLEs will use multiple GPUs when they can. There's also the question of an upcoming M-based Mac Pro. Clearly, the M1 GPU isn't a performance solution compared to the discrete options, which leaves 3 options. Add support for eGPUs, support for dedicated GPUs, or improve the M1. The performance hits on eGPUs are the least attractive, and honestly, I'm not sure how likely that would be rather than just straight up adding support for dedicated GPUs. On the other hand, Apple currently offers the add-on Afterburner card in its Mac Pros, so it's not entirely unreasonable that Apple will eventually add support for some means of accelerating video, either supporting its existing ecosystem or effectively offering extra MGPUs. The interesting question is, what is the future of Apple's homegrown silicon? What are they currently sitting on, and what will they have in a year? The oft-repeated rumors that Apple's planning a 128-core GPU for their professional line. The current M1 has up to 8 graphic cores. If they can scale that linearly, we'd be looking at a 15 times performance increase, or somewhere just ahead of the RTX 3080, and likely behind whatever NVIDIA's 2022 high-end card is. For comparison, a 16-core GPU scaled linearly would give you a 16% boost over the 16-inches Radeon Pro 5500M, and a 32-core GPU would get you 80% of the performance of the Radeon 7 based on single precision floating point operations. It's worth considering how to improve Darktable performance itself or any similar software. With Darktable, it's worth checking what GPU it's trying to use. I was surprised to find that on my MacBook Pro, 16-inch from 2019, it defaulted to the integrated GPU for most complex tasks rather than the Radeon. Swapping that was an instant performance improvement. With Darktable, there are either 2 or 3 different pipelines during the normal editing flow, and with enough GPUs, you can run each of those pipelines in parallel on a discrete card. In single monitor mode, you have the main editing window and the less demanding preview window. With a dual monitor mode, you can make use of 3 different GPUs to accelerate each of the main window, the secondary monitor display window, and the preview window. Multiple GPUs will also accelerate exports, or probably more importantly, the thumbnail generation on the light table. So fast floating point performance is key, but how much RAM? The Darktable documentation doesn't give good guidance, other than saying more is better. I only looked at 16 megapixel and 47 megapixel images, but since 100% of the 16 megapixel images fit under 4 gigabytes, and only a handful of the 47 megapixel images made it up to the 8 gigabyte mark, most users who are in the 20 to 50 megapixel range are probably going to be fairly safe with a standard 8 gigabyte amount of RAM. The lower end Sonnet eGPU, based on the Radeon RX 5500 XT, only has 4 GB, so I'd avoid that model. But if you can find a good deal and have an old 4 GB card to upgrade your machine just lying around, it'll be good for most of your 16 or 20 megapixel images, or honestly, really image at all if your only other option is the on GPU graphics. What's clear here is that you're not going to need all 24 GB of RAM on the NVIDIA RTX 3090. Although if you're shooting with the Fuji GFX 100 or your camera's high-res multi-shot mode, you'll fairly easily bust out of the 8 GB most cards offer, or even the 10 GB of the RTX 3080, meaning, well, you're going to have to bite that upgrade cost or find a lower performing 16 GB card like the Radeon 7. As promised, let's talk about some of the pros and cons of Mac OS. I'm not a huge fan of Mac OS, but I treat it effectively as an expediency for certain tasks. I actually still use that NUC for many things that are neither video nor photo-centric. Beyond commercial support, that is, a wider variety of programs and hardware, Mac OS does make managing multiple color-managed monitors easier. Single monitor setups for Linux aren't bad, but multiple different monitors with different profiles gets awkward. I left Linux when the color management daemon ColorD began to fail to work outside of GNOME. There are other options, but effectively it felt like the walls were closing in on me in Linux between systemd and GNOME. And, for ultimate performance, needing closed proprietary drivers again, I just gave in and switched to OS X for the situation where I needed video performance and color management. I figured in for a penny, in for a pound. Now, what are the drawbacks of Mac OS? Well, beyond being closed and proprietary, Apple has a record of changing things on software developers with minimal warning and no recourse. Remember when they switched ports between generations and suddenly your peripherals didn't work or removed a headphone port? Yeah, it's like that for developers too. My understanding is that's actually what did in Apple's own Aperture. Aperture relied on internal APIs they changed, necessitating effectively a full rewrite. Especially with OpenCL having been deprecated, there's real concern that Cupertino's already hung the sword over our heads. Okay, that was a lot of information. Where does that leave us? Well, honestly, I don't know. I can't find anyone selling a Tri-3090 system anymore, given shortages, and we don't actually know what the M-based Mac Pro will offer, let alone when it will appear. We don't know how Apple's MCPUs, GPUs, or unified memory architecture will scale. How much memory will it support? How will it perform as it scales out? And how much will it cost as it scales? At present, the clear performance option, if money is no object, is a dual or triple NVIDIA-based system, and it's likely that'll beat any Mac Pro option out next year. You're subject to NVIDIA proprietary drivers, but you're not going to be subject to the whims of Cupertino. I've also got other concerns since DaVinci Resolve on macOS has a few additional options, but I don't know that that'll be enough to push me over. I don't know what my next move will be. Let me know what you think in the comments. See you next time.